A bullet. Oops. Okay, so we've been looking at the stack and we realized that one of the things we got to attack first is transportation. So we were looking at how to engineer better cars to reduce the power that we use or energy that we use in driving cars. We looked at an equation last time that had a wind resistance term, a rolling resistance term, and a term that had to do with whether you're going uphill or downhill. Didn't we? Did I remember this wrong? Okay, I just want to make sure I actually covered that. So pushing the wind out of the way is wind resistance. That's given by this term here. Rho, again, is the density of air. A is the cross-sectional area of the front of the vehicle. You want to make that small. V is squared. That's your velocity, so you want to make that really small. The rolling resistance doesn't depend on how fast you're going, but it does depend on the mass of your car. This is a rolling resistance coefficient. This is gravity. We can't change that. And finally, we have the slope. So if you're going uphill, good. If you're going downhill, slope will be negative. You use less energy. Mass, gravity, this is the distance. And we need to include the energy efficiency, E, which isn't on this slide. So we looked at the wind resistance term last lecture, and we concluded that long, skinny vehicles was the way to go because we could reduce A. And driving slowly, reducing V, helps a lot, okay, if you're willing to do that, because the drag goes as V squared. So that's where we were last time. So here's steady speed, says driving at a constant speed, and let me point out that A, the effective area, is actually some drag coefficient times the actual area. So you can take a picture of the front of the car and put it on graph paper, not anymore, but back in the day, and calculate the actual cross-sectional front area of the car. But then the question is it streamlined or not? So the drag coefficient gives you a handle on what the effective area is. So an efficient car has a drag coefficient of maybe 0.25. The area of the vehicle, the real area, might be 2 square meters. So the effective area is a half a square meter. And it has 1 to 4 passengers, depending on whether you got the kids in the car. And so the area per person works out to about 0.12 to 0.5. That's an efficient car. A typical car might have a less good, I think the technical term is worse, drag coefficient, 0.33. Maybe it has a bigger cross-sectional area because it's typical, not efficient. You're not necessarily trying to reduce that. You get an effective area of 0.8, so now you've got more area per person. A bicycle is interesting. It has a very high drag coefficient, at least compared to stuff on this slide, 0.9, but the cross-sectional area is very small, 0.5 square meters. So the effective area is 0.45. You have 1 passenger. Area per person is not looking too good. But we will look at other aspects of bicycles shortly. A train is not all that streamlined compared to a car. It has a huge area, but it carries a boatload of people. So the effective area is 11, but if it has hundreds of people, it's less than 1/10 of a square meter. So trains are good, at least from an air resistance point of view. A bus, cross-sectional area, drag coefficient is about 0.45, area is 9, gives you effective area of 4, 20 to 50 passengers. How many people were on the bus today? Were there 20 to 50 on the, just you?
Probably 30.
20 to 30, so you guys are probably in about that range. So the area for a bike is big, but the velocity is small. And remember, the velocity is squared in that equation, so you get that's very helpful. A for a train is big, but again, it's shared by a lot of people. So let's talk more about the drag coefficient. So you know if you streamline something, it's going to have less drag. Streamlined vehicle reduces drag by reducing this coefficient. And the main thing you want to do is reduce turbulence. So here is a particular shape of a car, and you see all these swirls back here. That's an Indy car. Those swirls are turbulence. It takes energy to create that turbulence, and so you want to avoid that. If you took a sphere and threw it through the air, this is laminar flow here, meaning the air flows in layers, so these lines are parallel, but then here it gets turbulent. So a sphere has a drag coefficient of 0.07 to 0.05. Here's a Corvette, pretty streamlined, but at the very back you get some turbulence. Here's a bullet. a lot of turbulence. And here's your favorite thing, an airplane wing. Now we know why they're shaped like that. If you could shape your car like this, you'd have a very small drag coefficient, no turbulence. This says drag coefficient is 0.045. This is 0.295, 0.29, 0.07. So an airplane wing is pretty good. Here's the drag coefficient of a bunch of different shapes. So a sphere is almost a half sphere. So turbulence can form back here. It's actually worse than a real sphere. I think that's interesting. A cone is a cross-sectional area of a cone, a half. A cube is bad, pushing a big square through the air. Angled cube, a little bit better. This helps to break the air, but the air will come up here and then it will form turbulence behind here. Long cylinder, 0.82. Short cylinder, big. Streamlined body, ooh, that's our airplane wing again, 0.04. And a half a streamlined body looks like 0.09. I'm going to show you a vehicle later that looks a little bit like this. So you want to avoid turbulence. So if you have a design like this where the air flow stays laminar as it goes past the vehicle, that's good. This kind of shape will give you some turbulence. It won't be as good. Ooh, a movie. Corn syrup laminar flow. So laminar flow, again, is when the stuff, whatever it is, flows in layers.
Bring in red. Corn syrup dyed red. Now we're going to put in corn syrup dyed green. Now we're putting in blue corn syrup. All right, now we're going to rotate these fairly slowly 5 times. This one. Notice the flow is laminar because the Reynolds number is less than 1.
Reynolds number measures
This 2.
how streamlined it is.
This one.
And he's going slowly to avoid turbulence. And he's using corn syrup because it's viscous, so it'll be less likely to be turbulent.
4. 5. Now we're going to go back. Backwards 1. Backwards 2. Backwards 3. Backwards 4. Oh, I see. Very cool.
How cool is that? I would have never thought that would work in a million years. Laminar flow. Ooh! General Motors wind tunnel. I'm sure this is going to be great. This will show you how they do the testing on, unless of course we have to watch an ad. How do I get out of the ad?
We are here on our honeymoon.
Can I skip the ad?
Decided to take this trip.
This one you have to wait it out.
Huh?
You have to wait it out on the 30-second ones.
My husband Bucky
Fine.
was fully clear of
I'll talk over it so whatever they're trying to sell you, you won't buy it. Oh, cruises.
I don't know if we can all afford a cruise.
Yeah.
This month, General Motors is celebrating an important milestone in fuel economy. In response to the oil embargo of the 1970s and the introduction of federal fuel economy standards, GM built the world's largest wind tunnel dedicated to the design of automobiles. And for its 30th anniversary, we got to see how it works.
The wind tunnel is a large, closed loop tunnel, which means that the air continually recirculates. It's powered by a 4,500 horsepower fan that's 43 feet in diameter, and it can generate speeds up to 138 miles per hour here in the test section.
Engineers say there are 3 ways to improve a vehicle's gas mileage: reduce its weight, increase the efficiency of the powertrain, and improve the aerodynamics. GM credits the work done here with improving the aerodynamics of its passenger cars by 25%.
The wind tunnel was originally built for developing the aerodynamic shapes of our vehicles, and since it was built, we've also started working on wind noise reduction, make it quieter for people inside the vehicle. And we also measure the airflow through the front of the vehicle, which affects both the engine cooling and the air conditioning performance.
One of the latest advances from work done here will soon be available in the new 2011 Chevrolet Cruze Eco.
We have an innovative feature in this little opening, which is an active little louver system, which opens and closes based on closed. It provides a drag optimized solution and lowers the overall drag of the vehicle significantly for improved time and fuel economy.
This is the first application of the active shutter system on a compact car. It should help increase a vehicle's aerodynamic efficiency by 10% and will help this Cruze Eco achieve an expected 40 miles to the gallon on the highway. I'm Chris Hansen.
It's kind of cool how they do that. So, a couple of points. He mentioned those grills in the front. So when the grills are open, when the louvers are open, air can go in and cool the engine, but the engine is oddly shaped, and so you can get turbulence and it'll create drag in there. When the engine doesn't need cooling, they can close that and make it more streamlined. And there was something else I was going to say and I completely forgot, so maybe it'll occur to me later. The other thing about cars is when they're rushing through the air, you can create lift or you can create downforce. So lift is bad. It reduces the apparent weight of your vehicle, which could improve your rolling resistance and your slope business, but it reduces your traction, which is bad. Race cars actually are designed to produce a downforce, so they have their bumpers really low to the ground here so that air can't get underneath and provide any lift, and then they have these spoilers here which help to try to produce a downforce. This is a different kind of spoiler here. So those increase the rolling resistance, but they decrease they decrease your traction. No, sorry, increase your traction, but can decrease your air resistance. So downforce. So here's another example. Make the bumper low to the ground in the front, forces the air over the top, reduces the air moving below the vehicle, improves traction. This is really good in corners if you're a race car driver. But but it increases the drag, not decreases it. So if you're a race car driver, the point is to go fast. So your V squared term here is going to be very large. And if you're a race car driver, my guess is you don't care about saving fuel. But to save energy, do not go fast. Reduce this as much as possible and increase or decrease this as much as possible by reducing the drag coefficient here. At low speeds, of course, you're not worried about lift, especially if it's an actual car, so you don't worry about downforce. So things that can affect drag. If you have a very streamlined car, it'll be very efficient, but oh wait, you're going to grandma's house, you got to bring some luggage with you. The luggage rack will start to disturb that laminar flow, and that can increase the drag. And then if you put the luggage on, of course, that's bad. Although it's good when you get there and you need the stuff. Mud flaps, they keep your car cleaner, but they also disturb the airflow. So those can increase drag. And actually, even the shape of the wheel well matters. I don't know if you noticed in that wind tunnel, I don't know if it's that one or another one I'm going to show you shortly, the wheels are turning. And you say, well, what's the point of them turning? The car is in a wind tunnel and it's in a fixed position, but the rotating tires will affect how air moves through the wheel well. So even that can have an effect. Rear spoiler spoils the turbulent flow of air over cars. So it can improve your mileage by reducing drag, or some of them are just for show and it can actually make your mileage worse. And it depends on what you buy. Let's see what this wind tunnel thing looks like. I hope there's no ad. Oh, there is. I can skip the video in. You see the turbulence at the back. And here the tires are moving. Oh, spoiler. So there'll be air coming through underneath the car as well. Engineering is so much fun. Oh yeah, side mirrors. Well, they increase the frontal cross-section of your car, so that's bad. They increase safety, that's good. Here is a Model X electric car. This is a Tesla Motors. I don't know if it's real or if it's just a concept car at this point, but notice there's no mirrors. They actually have tiny cameras there, so it shows you the view from the mirrors, but inside. Improves the mileage. And increases the cost. Antennas. Antenna. Well, if you have a whip antenna, which is what many cars have, that disturbs the airflow also. This is called a shark fin antenna, and they're designed to reduce the turbulence and to be more efficient. Now they're embedding windshields in the, embedding the antennas in the windshields in some cars, so that's even better. That doesn't do anything to your cross section or your drag. Windshield wipers. Oh, here's one I never thought about, but of course those cars we were looking at, the windshield wipers weren't deployed. So you can have a windshield wiper like this, or you can use these low profile enclosed ones, which are perhaps better. So these are things you can do to your current car. Smooth wheel covers. Has anyone ever seen these? I was poking around on the internet. I've never seen this. But I found several pictures of them. The idea is to reduce the drag by a few %. On the other hand, some people say, well, the air can't circulate, so your brakes will overheat. Do I know the answer? No, I do not. So you would put these on eco cars, probably not on race cars. Have you guys seen those? Have you heard of them? Me either. Good, I'm not the only one. The bottom of the car can matter, especially if you're allowing air to circulate under there. Now, I have not crawled under my car lately, but I don't think it looks like this. I don't know what car this is. AutoZine.org, Technical School Aerotech. Now you know. Wipers, mirrors, trays, and spoilers can all help a little. But for maximum benefit, you want to reduce the area of the vehicle as well as the drag. So we're back to long, skinny cars. Remember I showed you before there was a teardrop shape was the best, and there was a half a teardrop shape. That's what this looks like to me. This looks like an electric car. I say that because it's enclosed and it's got a power cord, so I think it's an electric car. Automoto.com entry, eel eco car. It looks a little bit like an eel. 2 wheels in the back and 1 in the front. That way, whatever's in the road, you're guaranteed to hit it. Notice it's only 1 person wide, right? So we talked about that. I have not seen one of those on the road. Bicycles. So bicycles, the fuel for bicycles is your food that you want to eat anyway, so that's a good thing. The drag coefficient of a standard bike is 0.9. The area might be 0.35 meters square, so the effective area is 0.3. And a road bike might weigh 10 kilograms. A recumbent bike weighs a little bit more. It has the same drag coefficient, but it has less frontal area. So its effective area is smaller. Here's recumbent bike here. What's this? A low rider? I don't know what that is. Maybe that's this one.
I think you had those backwards.
I have them backwards. This is low rider?
Isn't the recumbent the middle one?
This one?
I think so.
Okay, could be. You're recumbent in both of them, so I don't know. I believe you. We have a faculty member in our department who has a recumbent. He had a neck problem or something, so he got a recumbent bicycle. It was like $1 million. And he would only take it out when the weather was pristine because he didn't want anything to happen to it. So we used to tease him about his gossamer bicycle. But anyways, the lowrider has a smaller drag coefficient, a small effective area, and therefore a small effective area, weighs 12 kilograms, and a streamliner bike, which I'm going to show you shortly, has a very low drag coefficient, medium area, very low effective area. Has anyone ever seen one of those? Me either. I would love to start seeing these things. Excuse me. So then I got to thinking about trucks. So I went online, imagine you're surprised, and I found this nice picture about trucks and a conventional truck. So if you got a double, what do you call this? Trailer? Huh? I forget, there's a name for these double trailer ones. This is drag coefficient here, and drag coefficient, this is 1, and this starts at 0.3. So cars are down here, 0.3 to 0.45. A van, a little bit higher. A bus, a little bit higher than that. Truck, standard truck like this. Notice this one's long. It has a range, and then this double tandem. So you're going to have problems with this gap. And then I found this, cab to container height. So here's the cab height, and here's the container height. And if you monkey with the ratio of those two things, and you've seen trucks going by that have all kinds of stuff on the top of the cab to make this thing more streamlined. But if you just have a discrete cab and a container, this is saying container to cab height ratio starts at 1.1. So the container is at least 10% higher than the cab. Here it's 40% higher. And we're plotting that against drag coefficient. Starts from 0.5 up to 0.75. And this is interesting. If you have a sharp roof edge, according to this, then as the container gets high, there's a bigger step here with respect to the cabin. Your drag coefficient actually goes down up until a certain point, and then it goes up again. That surprised me. The rounded roof edge, which I see a lot of on the road, where they have something on top of here. And I don't know if this is the roof edge of the cab or the container. I'm guessing it's the cab. They're saying a rounded one, and your drag coefficient actually increases as your container gets higher. And they say to minimize the gap between the cab and the truck. Here is gap width as a ratio to vehicle height. So the width to the height, and the drag coefficient, the scale goes from 0.5 to 1. So it's pretty constant here, and then when you get to a certain gap width, it starts to climb up. And I don't know why it starts to get better there. But this tells you how to design trucks for better efficiency. So I looked for fuel-efficient trucks, and I found these crazy pictures. I've never seen either one of these on the road. This one is just plain silly. I don't know. To me, that's as ugly as sin. What do you guys think? No, you like it? Oh, cool. All right. This is America. We can have a difference of opinion. Do you like this one? Yeah, I like this one.
This looks like a train.
It does. Maybe there is something to that. And this is goofy looking cab, but I guess there's a reason for it being streamlined. So I don't know why we're not seeing those guys. Here's the streamliner bicycle. So here, so you can see the inside. The guy, he's going to get a crick in his neck trying to look out front, but the case of it has a shape like that. He's recumbent, and over here he's got his foot down, so he's not going very fast. All right, so let's go back to our equation. The energy, we have the wind resistance. Oops, that isn't it. This is the wind resistance here. The next term we're going to look at is the rolling resistance. Notice it doesn't depend on speed. It does depend on the mass of your vehicle, and it depends on some whatever the CRR term is controlled by. So let's take a look at that. The rolling resistance happens because the primary thing is when you have a wheel and you are rolling along the road, the wheel is squishing. So it takes energy, the mass of your car is squishing that, and as you're rolling forward, you're squishing the next part of the tire, you're squishing, and as the tire rolls, the part that comes away from the road unsquishes, springs back. So some of that energy returns, but not all of it. So you get some energy used there. So I'm thinking maybe a stiffer tire that doesn't deform as much might be better. Rolling resistance also includes like the energy used in the bearings, the energy that goes in the noise, right? Nothing's free, so the noisier the tires, the more energy you're wasting. Energy that goes into grinding the rubber off the tires so it can be on the road, and then sweep into the gutters and plants get to eat it. Energy that goes into shaking the ground when the truck goes by, right? Energy that goes into squishing your shock absorbers when you go over bumps. There's energy in all those things. So that's all accounted for in the rolling resistance. Things that affect the rolling resistance, turns out if you use simple equations, the bigger the wheel is, the better the rolling resistance. Well, at least for rigid wheels. Like steel wheels on a train, so bigger wheels are better. It turns out that for car tires, it's not that big an effect. Speed, again. So the rolling resistance, we said the rolling resistance doesn't depend on speed, but that coefficient CRR, right? We don't see velocity in this equation, but this depends on your velocity. Surface adhesion, I want that, especially because it's going to snow this afternoon. The material of the tire, the depth of the tread. So when your tires get bald and you start sliding around more, you're saving energy just before you crash. The flex of the sidewalls. And I've seen tires recently where the, the wheel is actually fairly large and the tire is thin around it. So I'm wondering if that's to reduce flex of sidewall. Maybe it's just for show. Maybe it's just styling. Tire inflation makes a difference, and actually overinflating is just as bad as underinflating. An overinflated tire will skip over bumps and it'll change your tire's rotational speed, so there's some energy there, and it also reduces your traction. Underinflated, of course, you're deforming it even more. Do you believe? Yes, master. So here's some examples of the rolling resistance of some real wheels. Whoa! Train wheels, steel, on a steel track, 0.002. Trains are good. Very little rolling resistance. You've heard, I think it's going to show up on your midterm or in homework about some CSX train company says they can move, what is it, a ton of freight 500 miles on a gallon gasoline, some ridiculous thing. This is a contributing factor. Bicycle tire has a little bit higher rolling resistance, doesn't have much of a contact patch. Contact patch is the area of the tire that's in contact with the road. Anyone here ride a motorcycle? Yeah, so you know about contact patch, they teach you that. I'll tell you a story. A few years ago, I was in Brazil, taking a motorcycle trip in the countryside and out in the middle of nowhere on something that the tour guide called a road, but it was not. There were rocks and dirt and stuff, and the guy in front of me stalled suddenly. So I hit the brakes so I wouldn't hit him, and I didn't. But the guy behind me crashed into me, knocked me over. The guy behind him swerved around and ran over my leg. So I got a crush wound that's exactly a contact patch right on my leg. Right like that. And I gotta tell you this story. So I'm out in the middle of nowhere. My leg's not broken, great. So I ride the rest of the day. And I had some special traveling health insurance, so they flew me back and all that. So everything. But it turned out I had to have a skin graft because the motorcycle, weight of the motorcycle, because the guy was two up, he had two people on the bike. It was a big bike. Crushed all the flesh there and killed everything, including the skin. So they had to make a skin graft. So with a skin graft, what they do is they shave a piece of, you don't want to hear this probably, they shave a piece of skin off of someplace else, and then they sew it onto where you need. So they shave a half the thickness of your skin, and they sew it onto where your skin is dead. So I'm talking to the plastic surgeon who's doing this, and they use an instrument called a dermatome to shave the skin. It turns out that the most prevalent dermatome, the one that has the most market share, like 90%, is made in Northern Ohio by a company called Zimmer. And the engineer who worked on the dermatome that Zimmer made that they used in my skin graft was the guy in a motorcycle in front of me. No kidding. Ha! How cool is that? That's my story. All right, back to your regularly scheduled program. Contact patch, that's what brought that up. If you want to see the scar, I'll show it to you. Truck rubber tires, 0.007. Car rubber tires, 0.01. So I'm going to put steel wheels on my car. Maybe not. So let's do an example calculation. Let's say your car weighs 4,000 pounds. Let's say your rolling resistance is 0.01. Now the force, this is not the force to push the air. This is just the force to roll the tires down the road. Is the mass times the rolling resistance, and it works out to 40 pounds or about 18 kilograms. Now the power is the force times the speed. So if you're going 75 miles per hour, quick go to unit converter online, that's 33 meters per second. 18 kilograms times 13 meters is blah, blah, blah. Who cares? This is in MKS units. 7.8 horsepower goes into just squishing your tires so they can roll down the road. If you slow down from 75 to 55, the horsepower needed goes from 7.8 to 5.7. Speed again. The road surface matters. This really is a road. The place where I got run over by the motorcycle was not like this. It was considerably more potholes and rocks and vermin and stuff. So you want to stay off the gravel roads if you can. And let's look at this again. So you remember we had this plot last time. This is energy consumption in kilowatt hours per 100 kilometers. So it's normalized to distance is what we say. And this is speed in kilometers per hour. Kilometers per hour. So the assumptions that go into this graph, we use a simple theory, that equation we had. We go at steady speeds, so we weren't braking or anything. We assumed an engine efficiency of 1/4 at all speeds. We said that the drag coefficient times the area was a meter squared, just to compare all different things, 1,000 kilograms of mass. Rolling resistance is 0.01. And we see here that as your speed increases, your rolling resistance stays constant. The air resistance goes up as the square, so this looks like a parabola. And when you add this number to this number, here's 0 and this is this. Here's this plus this is that. That's your total resistance. How good is a simple theory? So the people who teach this course out in Colorado gave me this slide. I don't know where they got this data, but I don't know what's going on here. The Prius matches fairly well the expected data. BMW is crazy at low speeds. I have no idea why. Does anyone know anything about cars? Yeah?
I've actually always been told that around 45 miles an hour is the most efficient speed to drive a car, based on like all the factors combined. That the slower you go, like the engine's working harder, so it consumes less energy at a certain speed, but then it significantly drops off as you increase your speed.
Right. So, since you bring it up, at what speed, according to this, is the rolling resistance equal to the wind resistance? Give you a chance to look. Can you see it from where you're sitting? So do you think it's at 20 kilometers per hour? Do you think that the rolling resistance and the wind resistance are the same here? How about at 45 kilometers per hour?
Yeah.
Yeah? How about 60 kilometers? Anyone buying that? No, you're no fools. Right. So according to the simple theory, 45 kilometers per hour. And you said 45 miles per hour. So what are we missing? And you said it. What about the idling and the engine and all that stuff? Exactly. All right. Oh, we're back to bicycles again. At a steady speed of 20 kilometers per hour, that's 12 miles per hour, this bicycle uses 2.2 kilowatts per 100 kilometers. If it's an aerodynamic posture like this one, it's not me. When I'm on a bike, I'm yakking and I'm sitting up. But this guy, maybe it's 1.6 kilowatt hours per 100 kilometers. We got these numbers by plugging those into our simple equation, the one that we had. And here's a great scaling trick that engineers use. So when we want to compare things, we try to Well, I'll show you what we do. So let's look at the wind resistance. The energy expended to the wind resistance is, here was the first term in that long equation, and after the 3 terms, there was distance over epsilon, so the efficiency, so I brought that over. We convert that to energy per distance. So if I divide this by D, energy per distance, I get this, and then it works for any vehicle. I just plug in the A for the effective frontal area of the vehicle, which is the drag coefficient times the vehicle. And now I scale. So let's say I want to compare the bike to the car. So I take the energy per distance of the bike. Here's that equation, energy per distance. Here it is again. And I see that they both have the half, so I can cancel those. The resistance or the density of air is the same for both of those. And that leaves me with just this stuff. And then I just plug in the numbers. And I say, let's just say the efficiency is the same, 0.25. This comes from the book. Say the frontal area is 1/4 of the car's. Say the bike is not streamlined, so the drag coefficient, oh, I forgot I got these things. So we'll say the efficiency is the same. Frontal area of the bike compared to the car is 1/4. The bike is not streamlined, so it's 1/3, 3 times larger than the drag of a car. And the bike travels 1/5 the speed of the car. So I want to stick all that stuff in. I get 3%. 3/100. So the bike requires 3/100ths of the energy to go a given distance, even though it has more. One reason it benefits is the velocity. That's a huge thing. It has a bigger. We assume the same efficiency. Oh, this is the drag coefficient. It had a bigger drag coefficient in a smaller area, and still works out 3% of what it takes to drive a car. So what is the overall efficiency? Here are a bunch of ways you could travel and how many people are in the traveling device. Efficient car, 2 passengers, maybe 30 kilowatt hours per 100 person kilometers. So this isn't just distance, it's people distance. Typical car has 2 people, 68. So there's a big advantage just to going from a typical car to efficient car. Bicycle, wow. Not only that, but you're not burning gasoline, except for the gasoline used to make the fertilizer for the food you ate to power the bike. The train has hundreds of passengers, so it's very good. Bus has 50 passengers, still better than an efficient car. A plane, ooh, lots of passengers, very inefficient. You're basically throwing a huge hunk of steel up into the sky. Sea, now you got to plow through a bunch of water. So even though you have hundreds of people on there, you're still not that efficient. So if you want to solve the energy problem and by attacking transport, bikes and public transportation win. If you can get people to do it. But bikes are not good for taking the kids to daycare. You can carry some groceries on them. So cars are going to need something more to bring them back down into the reasonable range. Yeah. So, how can we convince people to buy more efficient cars? Here's some ideas. Maybe we could raise the price of fuel, like taxing. Could raise the showroom tax, I'd pay tax on new cars. So the ones that consume more fuel, you would make them pricier and discourage people from buying them. You could raise road taxes for inefficient vehicles, punishing people for having inefficient vehicles. Or maybe if you had an efficient car, you could actually park on this side of the river. Just saying. Fuel rationing. You could legislate effective vehicles. Are we doing that? Efficient vehicles?
We're doing pretty much everything on that list already.
To some extent, right? Are we legislating the frontal area and the weight? That we're not doing. Are we?
Not specifically.
Not directly.
Inadvertently.
Yeah.
Or I don't know.
Indirectly we are.
Yeah, indirectly.
Yeah. Are our road taxes higher for inefficient vehicles? I don't know if we're doing that one. I don't know how you do that one.
Well, they're giving a tax break if you have efficient vehicles.
On your income tax?
Yeah. If you make above a certain amount, of course, because of the deduction. So I guess you could technically say, not technically, but you know, if you're above a certain pay grade, then it would apply, I guess.
So that's discouraging. We're already doing all this stuff.
Need to make them more enjoyable to drive.
Make it more enjoyable to drive? That's an
Basically,
idea.
Fun to drive.
Huh?
Tesla 4?
Yeah, Tesla's also like $100,000.
Is it a real car, that Tesla one that exists?
Oh,
They're
well,
awesome.
I don't know about that specific one.
Oh.
They have the Tesla Model T
Yeah?
that
The Model
is
S.
like over $100,000, but it gets like I don't know how you would gauge what it gets. It's electric, but it's fast.
Hmm.
That and the Karma Fisker,
Yeah, that
but
one
those are all like
explodes.
Explodes? That
Oh,
does make it more exciting.
yeah.
That one is not nearly as good as but it's about twice as expensive as the Teslas too.
Really?
Yeah,
Wow.
they're putting solar panels on the top of the car too. So
We could lower speed limits. When I was young, we didn't have this 55. Speed limits were all 65, 70. Now then we reduced them to 55 and people screamed. They didn't want to, even during the energy crisis, I guess the first one was. And now many states, West Virginia's up to 70. Out west, there's lots of places where it's up to 70 because they have so far to go. People just couldn't stand to go that slow, period. We're hogs, we have to have our lifestyle. We could reduce congestion to reduce stopping and starting. That would help. You said make driving more enjoyable, right? Maybe if we made driving less enjoyable, people wouldn't do it as much, but maybe we made it more enjoyable by reducing starting and stopping. And our next lecture is going to be on starting and stopping. So we could have bigger highways. They're going to finish the Route 71, Interstate 71 between here and Cleveland. There's a patch that's not 3 lanes yet. They're going to finish that by 2015 or something. I can't wait. I go that way when I come home from Christmas and I get jammed up there. Put 50 people on one vehicle, public transportation. Yes, we should do that. And you guys are students. You're taking the buses all the time. But hideous old people like me, we live out in the suburbs. We don't want to take a bus. It's going to take me an hour. I have to go downtown, and there'll be icky people on the bus with me. This is though what we need to do. Have more fun driving. Have other vehicles near me sensors. Maybe tax you for driving in congestion. This is your incentive to drive not during rush hour, if your boss will let you, so that you're not starting and stopping as much. Again, starting and stopping will be the topic of our next lecture. So we found what we need is long, skinny vehicles that are very aerodynamic. You want your kids behind you, not next to you. Multiple passengers per vehicle, so the more kids you have, the more efficient you are. No, wait, that can't be right. Drive slow. This is a huge deal. Up to a point. If you drive too slow, engine idling and rolling resistance is no benefit. These results are arrived at by considering steady state driving, so at a constant speed. Rolling resistance is not negligible. It becomes more important when you're going slowly. You have to trade off rolling resistance with traction, especially if you have kids. You want to have traction, that's important. Steel wheels and big diameters are the best, but they won't let me drive steel wheels on the roads on 670. I don't think so. So summary is, for long distance trips, energy is dominated by wind resistance. We can improve that if we get more streamlined, get a lot of people to share your vehicle with you, go slower. Even with the best streamlining, cars are still inefficient compared to other kinds of transportation. And then our next lecture, we'll talk about short distance trips, starting and stopping. Are there any questions? Yay! All right, run and play. Thanks for playing our game. Oh, did I press start? Yes.